thank you very much. Unfortunately, I sort of hate to go after that because I won't be nearly as good of a lecture as that first one. So that's good to go first yesterday, so that I don't have anyone that I can be compared to. So anyway, so I'm going to continue my discussion of the mapping class group. So I'll recall my notation as I discuss it. So let's let H here be the first homology group of our genus G surface. So that right there, of course, is Z to the 2G. So the mapping class group, mod sub G, remember that's the group of orientation-preserving diffeomorphisms of the surface up to homotopy. So that acts on H. That's just sort of how homology works, right? Homology is functorial, and it's a homotopy functor. And so, but this is not. There's some extra structure here. So this preserves what's called the algebraic intersection pairing, which is a pairing omega going from H, it's a bilinear form, H cross H to Z. Just to remind you of how this thing works, right? For example, we have, here is a genus 2 surface. Let's just write down a couple, homology classes. So let's say that right there is X. Sorry, my handwriting is not very good. Say that right there with that orientation is X. And then let's say that, so we're going to go like up there. Say that with that orientation is Y. So what is, I should use different colors. What's omega of xy? Well, each intersection has a sign, right? And so what are the intersections? There's that intersection right there. And what's the sign of that? Well, x is going that way and y is going that way. So that gets a -1. Then it goes, let's see, where the next intersection is right there. In that case, it's the same thing. That's also a -1. Then it goes around here. Here, x is going that way and y is going that way. So that gets a +1. And it goes, and then here we have our final intersection. That right there is also a -1. And so therefore, this right here is -1, -1, +1, -1. So that right there looks to me like -3 + 1 is -2. Okay, so we just, for every intersection of the two cycles, you look at the sign of the intersection, you add up those plus minus ones. So what are some properties? So omega, well, is a symplectic form. What does that mean? That means two things. First, it's alternating. So if you flip the inputs, you get a sign. So it becomes -1. It's also non-degenerate, which means that it induces an isomorphism between H and its dual. So if you have any bilinear form on a vector space or a Z module, you get a map from that thing to its dual, right? And so non-degeneracy means that it induces an isomorphism there. This is a statement of Poincare duality. So this right here, this is like literally Poincare. Okay, and so we have a map, an action of the mapping class group on H, which preserves a symplectic form. And so this gives us a representation that goes from the mapping class group to the automorphisms of H, preserving that form. And that right there is SP 2G of Z. Okay, so we have a homomorphism from the mapping class group to the symplectic group, the integral symplectic group. This turns out, this is very classical. That's a surjective homomorphism right there. And so this is, I think of this as a sort of first order piece of information about the mapping class group. So this right here is, this is an isomorphism for G is equal to 0. Well, that's pretty stupid. The mapping class group is trivial and the symplectic group is trivial. So, and G is equal to 1. The mapping class group of a torus is, well, SP2 of Z is the same as SL2Z. So that's just saying the mapping class group of a torus is SL2Z, but not for G at least 2. And I'll give you examples of elements in its kernel in a few minutes. Okay, so this is, you know, from an algebra topological point of view, this is the first thing you would think about to try to get information, to detect non-trivial elements of the mapping class group. You know, the symplectic group is a group of matrices. We can multiply things in there. It's very easy to work with. A mapping class group is not a group of matrices. It's actually open whether there's a linear representation. And if there is, it's probably such a mess that it's worthless. Like worthless, maybe not theoretically, but worthless like for calculating. Yeah, this map is definitely surjective. That's a class that goes back to the 19th century. So, and it's not difficult. One way to see it is that the symplectic group is generated by transvections, integral transvections, and Dane twists go to transvections, and so you hit all the generators. So this gives you you know, the first thing that you might think about looking at. So the real topic of these lectures is the kernel of this representation. So definition. The Torelli group is the kernel of this representation, so of the action of the mapping class group on the first homology group of the surface. So it's the group of mapping classes that act trivially on homology, the things that are invisible to this representation. And so we have, you know, this short exact sequence. One goes to Torelli G. Why it's, oh, I forgot, it's denoted for reasons I don't want to go into with a script I. I'm sorry, it's not T sub G. Well, T sub G is Teichmuller space, so I can't use T sub G. And so I is the obvious next choice, right? So one goes to this notation is not, I'm not responsible for it. I apologize. So as I sub G, the mapping class group, of course, I'm already using sort of strange notation. The mapping class group is mod sub G. You can blame Benson Farber on that. He browbeat me into saying that, you know, it's not MCG that looks like Miller genuine draft. You know, it's mod sub G. And then that goes to the symplectic group. Okay, so we have this short exact sequence. We want to understand things about it. So the first thing I want to do is I want to give you some elements of the Torelli group because I want to prove that it's non-trivial. And so remember, if X is a simple closed curve on sigma G, so then we have the Dane twist. So T sub X, which, you know, I'm just redrawing this picture that I drew last time. You have this transversal curve right there, and it goes to something like this. And so how does this Dane twist act on homology? I already sort of said it in words, it acts by a transvection. But what's happening is if you have any cycle, every time you hit X, you pick up a copy of X, right? You're adding to every cycle on the surface, the Dane twist is adding a bunch of copies of X. If you cross it in one direction, you get a positive, and you cross the other direction, you get a negative. So you could write down a formula for that. The formula involves, well, you choose an orientation on X, you look at the algebraic intersection pairing, that tells you how many copies to add. But the really important thing is that the effect, the action of the Dane twist of X around X on H only depends on the element of homology that's defined by X, say, you know. So the Dane twist doesn't depend on orientation, but let's just choose an orientation so we can make sense of what element of homology X corresponds to. Okay, so that tells us how to write down some elements of the mapping of the Torelli group. So for instance, here are two obvious things you can do. So for example, so if the homology class is 0, but what does that mean? So i.e., so x is a separating curve. Then the Dane twist about x lies inside Torelli group. So we have elements of the Torelli group, say, that look like this. And so there's the Dane twist about that x lies inside the genus 2 Torelli group, because you're adding every time when you Dane twist about it, every cycle you're adding a bunch of copies of x to that cycle, but x is 0 in homology, so it doesn't do anything. I mean, another way you could see that for this particular picture is you could write your standard basis for homology. You have a loop there, a loop there, a loop there, a loop there. It's literally not touching any of those basis elements. So that's one. So now we see that in genus 2, the Torelli group is not a trivial group. Like, there are elements inside it. There's another slightly more sophisticated thing you could do. So here's an example. So if x and y are homologous curves, then so the Dane twist about x and the Dane twist about y do the same to h, right? The same thing in homology. So this means, so x equals y, so if, or I should say, if so x and y are disjoint and they're homologous, so then their union, so bounds, so a subsurface. So the picture looks like this. We need at least genus 3 to draw a picture like this. So there's one curve x, and there's another curve y right there. And we see then that in this case, because these are doing the same thing to homology, if we do the Dane twist about x, and then we do the Dane twist about y inverse, we're doing something to homology, and then we're undoing it, right? And so therefore, that's inside the Torelli group. Okay, so these things have names. These are separating twists. And these, because it's a pair of things that bound a subsurface, these are called bounding pair maps. Okay, so those are the sort of basic elements of the Torelli group in the same way that the Dane twist is the basic element of the mapping class group. And one reason for that is that we have the following theorem. This was due, so like a large percentage of this is an enormous calculation that was done by Berman like in the early 60s, or maybe late 60s, and then completed by her student Jerry Powell, that says that Torelli G is generated by separating twists and bounding pair maps. So we usually sometimes call those BP maps, and BP maps. So this was this gives you generators. By the way, so Powell, soon after, he wrote a beautiful PhD thesis, and he did some excellent early work on mapping class groups of 3 manifolds and stuff. And then he entered a monastery and hasn't been heard from since. So what I was told by Joan Berman was that apparently I think his sister was quite ill, and he made a vow to God that he would enter a monastery if she was healed, and she was. She thinks it's a gigantic waste, but I might have other opinions. I'm glad that we have someone praying for the Torelli group. Yes, I believe so. Yeah. No. No. Berman thought him entering the monastery and leaving mathematics was the waste. So This is her student. So anyway, yeah. Yeah? No, no, no. It's only homotopy to the identity if X were itself homotopy to a point, right? But this is not homotopy to a point. It cuts the surface. On either side of it, you have a torus, right? So this is definitely a non-trivial element of the mapping class group. But that's not the homotopy. That's moving a thing in space. We're not homotoping in space. We're holding the surface fixed and just deforming it like it's made of rubber held on a cage in space. Any other questions? Okay, so we have those theorems right there. So now this, I stated this carefully. I did not say it's finitely generated, right? I said that it's generated by separating twists and bounding pair maps. There are infinitely many. There's many, if you're not someone that spends a lot of time in the land of surfaces, you might think that all separating curves look like this. But in fact, like a typical separating curve, it kind of goes all over the surface. That's really a sort of technical way of dancing, what a separating curve looks like. But there's infinitely many. If you saw it, it would look like it was just sort of parallel strands passing everywhere, kind of, you wouldn't even be able to tell it's separating, if you saw it. You wouldn't even be, you'd have to spend a lot of time following it carefully to make sure it was a single curve and not 7 curves, right? Okay, so this is an infinite generating set right there. And in fact, since the Torelli group, so is an infinite index subgroup of the mapping class group. And so this implies is that, so even though sub G has, all possible finiteness properties. So it's finitely presented. All of its homology groups are finite dimensional, and so on, right? So we argued that followed from algebraic geometry last time. Nothing need hold. We don't expect anything. Expect the same for Torelli. When you pass from a group to an infinite index subgroup, it's very special if any finiteness properties are retained. Typically, they're not. An example. So again, if you don't spend your lives thinking about groups, you might think you pass to a smaller object, it gets smaller, right? But of course, in group theory, that's not true. For example, so if we take the commutator subgroup of the free group on 2 generators, this is an infinite rank free group. And we know that by covering space theory. So this is a thing you teach in basic algebraic topology, right? So this is there's the free group on 2 generators. It's pi1 of that wedge of circles, and the associated covering space is this infinite grid going in all directions in R2. It's the grid inside R2 whose one of whose coordinates is an integer, right? So either the x or the y coordinates is an integer right there. And so this right here, this curve right there, if that's A, that wraps around all the horizontal ones. That's B, that wraps around all the vertical ones. So it's that infinite grid right there. So therefore, in the land of group theory, of non-abelian group theory, passing to subgroups typically makes the groups get much bigger. It's a very perverse feature of the theory of groups. And so you see, even though F2 is a very small group, its commutator subgroup is a very big group. And so that's the sort of thing you expect to hold, I think, when you pass to infinite index subgroups of groups. And in fact, that holds something, in fact, it is definitely true that we lose finiteness properties when you pass to Torelli. So here is a theorem. This is Jeff Mess's PhD thesis. And what does this say? This is theorem. Mess. This says that in genus 2, the genus 2 Torelli group is an infinite rank free group. you know, of all the groups it has, you know, that it could be. That's what it is right there. So I don't have time to give you the complete proof of this right here, but I want to say something about it. The proof of this, you remember I spent all that time on algebraic geometry last time. The proof of this actually uses algebraic geometry. So the proof, it constructs a K Torelli 2-1 using classical algebraic geometry. So special features of genus 2 algebraic curves and their Jacobians, which, and as an audience of topologists, I don't want to give you a short course in algebraic geometry to explain what goes into it, but I want to give you a toy model. I want to give you the flavor of the kind of space that he constructs. Okay, so here is a sort of toy model, because there's a lot of algebraic geometry, but then there's one beautiful argument at the end of the thesis, which you can put in a simpler context, and I think is very cool. So I'll just, here's the flavor of the kind of space. I think of it as a sort of toy model. So here is a much simpler space that has some of the same features as the one he constructs. Let's let L, right there, this is a set of disjoint lines in R3, okay? And so then what I claim, so here is something, and this is let's say an infinite set, right? So it's not a finite set. The claim is that the fundamental group pi1 of R3 minus L, so is a free group. So of rank, the number of components inside L, which is infinite if L has infinitely many components. Now, there's many ways to prove this. Like if L has just like there's just 3 lines, you often give this as an exercise in algebraic topology class. But when you're trying to deal with infinitely many, that becomes kind of trying to triangulate these things, or deformation track becomes a little complicated. Mess gives a really beautiful argument using Morse theory, which I just want to tell you because it's so pretty, right? So here is a Morse theory argument for this. And then I'll tell you sort of how he generalizes this just very briefly, like how this is related to what he does. So here's the proof. Use Morse theory. So let's pick some point x naught inside R3 minus L, and we'll say let B sub R equal the ball of radius R around x naught in R3 minus L. And so here's a question for you. So as R goes to infinity, when does the topology of BR change? Well, we have this increasing ball, right? So it starts off disjoint from all the lines. The first time it changes is when it becomes tangent to one of these lines, right? So, and every time it becomes tangent to the line, to a new line, something happens, right? So the topology changes each time the boundary of B sub R is tangent to some line inside L, and I can't draw a 3-dimensional. I'm not really a great, right? So, but here is like the 2-dimensional picture right here. Let's say we're looking down, the line is vertical. Okay, so if this right here is L, right? And so this right over point right here is, the increasing balls, they look like this. That's just normally happening. And then when it passes there, what's going to happen is, well, we have it's pierced right there, right? You attach a one handle. Because you see, like, you get a, you get a new loop that goes around this line. Like you have a new generator that goes like this. You attach a one handle, get a new generator for pi 1, okay? And so that's what happens. And so that's the proof, is every time these balls get bigger and bigger, each time you pass through one of these lines, you attach a one handle, and you get a bigger free group. And just if there's infinite many lines, you get an infinite rank free group. Now, this doesn't look like it has anything to do with the Torelli group, right? So what do we use? So this uses, we don't add, I didn't use that many features of R3 and lines, right? So this uses two things. This uses only, well, what we need that these balls become tangent to a line only once, right? So as they'd only pass through a line once, and they never loop back around and pass through a line again, right? And so that uses only the fact that R3 has non-positive curvature. So and is contractible. So, and the fact that each L inside L is a codimension 2 totally geodesic subspace. If you have such a collection, you have some kind of non-positively curved contractible manifold and a collection of disjoint totally geodesic codimension 2 subspaces. The complement has fundamental group and infinite free group in bijection with the components. And by the same argument, you should look at increasing balls. Every time they become tangent to each of them exactly once, they pass through it and you attach a one handle. And that's exactly what Jeff does, what Mess does. He constructs such a space using algebraic geometry. So what Mess does, using classical algebraic geometry, so Mess constructs a K gamma G gamma 2 1, so as the complement of infinitely many totally geodesic subspaces well, you expect there to have something to do, totally geodesic subspaces of codimension 2 so this should have something to do with the symplectic group, right? And it's in the symmetric space for the symplectic group. So in the symmetric space for SP4 of R. So if you don't know about symmetric spaces, don't worry. I'm not going to talk about them again. But they're generalizations of the hyperbolic plane. The hyperbolic plane is the symmetric space for, say, PSL2R. Okay, and so associated to any Lie group, you have some sort of nice non-positively curved Riemannian manifold, called a symmetric space. And so inside, since you expect the Torelli group in genus 2 to have something to do with SP2G's SP4Z, this is the fact that the space for this appears is maybe not so shocking. That's just a teaser to suggest Mess's paper. It's really an impressive assemblage of facts. Okay? So any questions about that? That's all I want to say about that. That's my last mention, I promise, of algebraic geometry in these lectures. Mostly I wanted to give this picture right there, because I think that Morse theory argument is quite beautiful. Okay, so hopefully I've convinced you that the Torelli group, not only should it have no finiteness properties, but it probably doesn't, right? Like an infinite rank free group, it's a very non-finite group, right? It has, it's pretty bad. And this has been generalized. So, there's how about higher genus, like genus things? What happens in higher genus? And so this is generalized. Here is the generalization. So we have the following theorem. This is due to Besvina, Bux, and Margalit. And they proved part of this, and Guy-Fulin proved the rest. What they proved is that for G at least 2, if we look at the dth homology group of the Torelli group with Q coefficients, this is infinite dimensional. And I have to copy this down, for 2G minus 3 is less than or equal to D is less than or equal to 3G minus 5. So you notice that if you plug in genus 2, this reduces to saying H1 is infinite dimensional, right? So that's this 4 minus 3 is 1, 6 minus 5 is 1. So this generalizes that lack of finiteness to sort of higher homology groups. And so passing, while the, oh, and by the way, what's the significance here of this 3G minus 5? So this right here is the cohomological dimension of the Torelli group. That's the theorem of Besvina, Bux, and Margalit. That's part of what they do. And what they show is that that's the cohomological dimension, and in this degree, that homology is dimensional. And then and they conjectured actually almost exactly this range, and Guy-Fulin proved it. So that's that right there. So this doesn't have a lack of finiteness properties, but there's something conspicuously sort of lacking here, right? So this says, this is really sort of higher dimensional homology. How about lower dimensional homology? What do we know in that case right there? So in particular, starting in genus, this doesn't say anything about H1, right? Or H2. So we have the following theorem, which to me is an extraordinarily striking result, and I'll say why. So this is a theorem of Dennis Johnson. So on the other hand, this is in the early 80s, I think maybe 83. Actually, Johnson's theorem came before Mess's theorem. Mess's theorem is in the late 80s, like 89 or something like that. I think it was published in 91. Yes? Yeah. Yeah, so HD, so finite generation has something to do with H1. If you're finitely generated, then H1 is finite dimensional. Yeah. So if you're finitely presented, H1 and H2 have to be finite dimensional. So presentation has got something. So generators have something to do with H1. Relations have something to do with H2.
So this says nothing about whether it's finitely generated.
That's right. Exactly. Yeah. It says nothing about that. This says nothing about finite generation or finite presentation, and that's good because of the theorem I'm about to state. Yeah. So the theorem I'm about to state says for G at least 3, G is finitely generated. So it's good that these two theorems do not contradict each other. That would be bad news, right? Then we'd have more interesting things to talk about, the sort of self-contradiction of ZFC or something like that, right? So no, so being finitely generated implies that H1 is finite dimensional. But the converse is not true. You can have groups like, for instance, if you look at the if you have a compact manifold and you look at diff naught, the identity component of the diffeomorphism group, that turns out to have trivial H1, but it's like an uncountable group. It's definitely not finitely generated, right? So there's a sort of, if you're finitely generated, then H1 is finite dimensional, but the converse is extremely false. If you're finitely presented, H2 is finite dimensional and H1, but the converse is false, you know. So that's, then for the higher dimensional homology groups, there's not such a clear group theoretic meaning. They're just properties of a k-pi1 for the group, you know, in the same way that, you know, if you have a space, it's, the fundamental group is finitely presented, you know, one way to see that is if its two skeleton is compact, right? That's the same thing as finitely many generators and finitely many relations. Okay. So we have this remarkable theorem right there. This is, and the theorem is, the proof is not conceptual at all. What Johnson does is he writes down an enormous generating set. You know, it's got exponentially many elements. Once you get to GNS like 10, it's got billions of elements. I mean, how do you even write down a billion mapping classes, you know, on a surface? It's this very complicated inductive procedure. And then basically by brute force, he shows they generate them. They generate. You know, what he does is he shows that, well, he looks at the subgroup that they generate, and he shows by like carefully conjugating them by generators of the mapping class group that it generates a normal subgroup. You know, there's like some like giant complicated inductive proof to that. And then, but they normally generate it by Berman-Powell. So that's what he does. It's a total. If you don't have to remember that. It's just a complete. It's a calculation. It gives no insight into like why magically this happens. So to my mind, this is still a very mysterious theorem. By the way, so this is also, as far as I know, this is the only annals paper that's ever been written by a homeless person. So when Dennis Johnson wrote this paper, he was living in the woods in California in like a trailer, like a van or something like that. Because he had a PhD in math, but his true passions were kayaking and mountain climbing. And so, you know, he would work for a month or two at JPL and then spend the rest of the time living in the woods of California. But he was friends with Rob Kirby and Joan Berman, and so they would like encourage him to, you know, submit his mathematics and distribute it. So he's a very interesting person. He got a full New York Times obituary a few years ago when he passed away, but the obituary barely mentioned his mathematics. So he got an obituary for his contributions to minimalist music. So because apparently he was the inventor of minimalist music, which doesn't make any sense. That sounds wrong. But apparently Lamont Young, who's usually that's, you know, he's considered one of the first people to write a piece of minimalist music, actually said no, his roommate in college, this guy Dennis Johnson, who he lost track of, actually invented minimalist and wrote the first minimalist piece of music, and they just rediscovered the score a few years before Dennis died, and they recorded it and it won a bunch of awards. So we got this full New York Times obituary, and the last paragraph said, oh yeah, he also had a PhD in math and invented this Johnson homomorphism that people still care about. So he is, you know, the most interesting man in the world. You know, that's all I can say about that. I think I heard a story, I think from Rob, that, you know, he liked to kayak, but he didn't like to know that someone had kayaked things before. Not because like he wanted to win, like that wasn't important, but because if he knew it was survivable, then it wouldn't be fun anymore. So, like he had to like if he knew that he was going to survive, like it brought him no pleasure. So, anyway, so that's that right there. Here's an open question. It's still open. So Torelli finitely presented? That's a notorious open question. It's very, you know, it's been open since the 80s. Really, it's been open since the 70s. I think Berman asked questions related to this even before we knew it was finitely generated. You know, she was asking things like this. So this is a notorious open question. I have no idea. And so H2 of Torelli with integer coefficients finitely generated. That would be a weaker statement than being finitely presented. Again, I don't know. You know, that's a notorious open question. On the other hand, I do know something. So this is the excuse for giving this lecture series, is the following theorem. So theorem, this is myself with Dan Minahan. I'll be optimistic and say 24. It might be 25. We'll find out when the paper actually gets released. So what we do is we calculate H2 of Torelli, unfortunately not with the integer coefficient, but with rational coefficients for G at least 6. It is, and show is finite dimensional. So we can't deal with the integer coefficients, but with rational coefficients, we can in fact calculate it. And so it has many more features than being finite dimensional. So what I want to do is I want to explain to you, that's the sort of game, like the sort of thing that I want to do in the remaining 2 and 2 1/3 lectures. So is I want to explain something about this. So because there's a new mechanism here. So I think before I used to publicly conjecture that H2 was probably infinite dimensional. And the reason for that is that I'm a pessimist. I sort of don't believe anything, right? And so I thought there was no reason even for it to be finitely generated. I thought that this was just a bizarro fluke, right? And so my goal for the remaining lectures is I want to explain, well, there's a mechanism here. So I want to explain a new mechanism for proving finiteness results. Oh, I should say remark. So this earlier, Minahan proved that sure that's finite dimensional for G exactly greater than or equal to, what's the number? It's exactly the number you expect, 51. So by a sort of primitive version of what we ended up doing. So we figured out how to improve this to get the sort of correct genus bounds probably, but also to get much more sort of much more information about it in a way that allowed us to actually complete the calculation. So his gave no information except for finite dimensionality, the sort of version that he gave. So the remaining lectures, I want to give a new mechanism for proving, well, there's sort of two things. So for proving, finite dimensional, and well, there's another result that goes into this that's an algebraicity result, which I'll explain. So algebraicity results of this flavor. And I want to illustrate it. So I told you that Johnson's theorem the proof is not conceptual. The proof is a gigantic calculation. And I want to be able to, and later on, I'll explain Johnson calculated H1 of the Torelli group, but his calculation depended upon proving finite dimension, proving finite generation first, depended upon delicate features of his actual generating set. So results of this flavor, illustrating it with, well, so the proof of this is quite complicated. It'll probably be about 100 pages. But I'm going to illustrate this by explaining how to do this, how to calculate H1 by like this, which the proof comes just almost by pure thought. So it involves almost no calculations. So illustrating by showing how to, show that H1 of Torelli G with rational coefficients is finite dimensional for G at least 3. And as I said, in a way that somehow it's sort of different, like it proves much less than what Johnson did. So Johnson, as I said, he later on calculated H1, but he needed this very complicated finite generating set. So it used all these very delicate calculations until you got to the end of the proof. You had no idea if it was going to work or not. But here there's a mechanism you'll see that somehow it lets you prove all sorts of results along these lines, almost, and it's like without having to really think. So it's sort of an abstract mechanism, and it's and it fits into the theme of these lectures. So it fits in to what Christine was talking about. So this has a representation stability flavor. Okay, I'll explain what I mean by that. So that's what I'm going to do with this. So are there any questions about that before in the last 15 minutes, what I want to do is I want to explain how Johnson, what form Johnson's calculation of H1 of Torelli took. So yes. Yeah. Calculate, well, okay, I'll explain these things are representations of the symplectic group. We can write down what representation it is. So like it's a complete calculation. So certainly like you can write down its dimension using our thing, like as a vector space, but in fact we calculate it as a representation of the symplectic group, and that's actually quite important for how the calculation works. So any other questions? That's what I mean by algebra results. That plays a big role in understanding the symplectic representation theory of this. So that's what I want to talk about. And so let me explain what form does H1 of the Torelli group take. Well, so Johnson, after he proved that Torelli was finitely generated, he calculated its abelianization. He calculated H1. There's a lot of very interesting torsion. And I can't say anything about torsion. Like our techniques are sort of fundamentally rational techniques. So, well, if you want to calculate things, so like there's sort of parts of it can give you rational, can give you torsion information, but you're not going to be able to calculate things. You're not going to be able to calculate torsion using our techniques. So, but the rational part of the abelianization of H actually has quite a beautiful description. And so here is the last thing I want to talk about in this lecture is what's called the Johnson homomorphism. Okay, so now I'm going to have to do something, I have to apologize slightly. So I've been talking about closed surfaces, and the reason I've been talking about closed surfaces is I think of closed surfaces as the real fundamental things you care about in the mapping class group. There's also, as we've seen in the other lectures, surfaces with boundaries, surfaces with punctures, and so on. I think of those as sort of technical tools you need to study the thing you really care about. But for this, it's much more convenient to work with surfaces with one boundary component, and so I'm going to do it there. So henceforth, we'll study, so mod, and I always put this mod G1 and Torelli G1. These are, so i.e. one boundary component. So it looks like this. As I said, because there's results for closed surfaces and for surface and so on, but the statement for the abelianization takes a much nicer form for surfaces one boundary. Okay, so I want to recall that so let's see here. So recall that H here, well, that's H1. Well, I have a surface with one boundary. Like that doesn't actually change anything. It's still z to the 2g. The superscript means boundary components. Yeah. So here I demand, identity on the boundary. That's right, yeah. It's diffeomorphisms, orientation preserving of the surface that fix the boundary pointwise, up to homotopies of the same form. And by the way, I apologize. I know the other lectures put boundary points here. Algebraic geometers always talk about mg in, like they put number of mark points in the subscript, and so I'm going to stick with the algebraic geometry. I absorb their conventions, and so I can't do otherwise. And so they always put the punctures in the subscripts, and they never talk about boundary components, so that's why you put them in the superscripts. So anyway, so it doesn't actually change H1. H1 is still z to the 2g, right? So it's pretty mild here. And so here is what Johnson proved. This is a theorem of, Johnson. So Johnson. And so I'm going to construct this isomorphism next time. But what did he prove? He proved that for 3, we have that H1 of Torelli G1 with Q coefficients is isomorphic to wedge 3 of H. To put, let's say that this right here, I'll put, let's say this is Q coefficients. What he really showed was H1 with integer coefficients modulo torsion is wedge 3 of H. Oh, that's an integral statement, but this is what I want to show. Okay. And so there's more structure here than you might think. And so let me explain. So here, let me make, first, here's a remark, by the way. So I never told you what H1 of the mapping class group was, did I? So H1 of the mapping class group is trivial for G at least 3. So nota bene, so for G at least 3, H1 of the mapping class group 1 with integer coefficients, that, by the way, is the same thing as mod G1, its abelianization. That's trivial. And why is that? So remember, there's 2 facts. So first, we have that the mapping class group mod G1 is generated by Dane twist T sub x with x a non-separating simple closed curve. That, remember, I even drew that generating set last time. We don't need, like this says we need, all of those. That's all that, that we just need, that, and that. Okay? Generated by Dane twist about x with x a non-separating simple closed curve. But here is the This is AB for abelianization. ABELIANIZATION. So, sorry. So, which I'm going to call AB from here on, okay? Yeah. So, my handwriting is awful. So, so it's generated by Dane twists about non-separating simple closed curve. The other fact, so B, so if for non-separating simple closed curves x and y, so there exists, so a map f from sigma g to sigma g, so diffeomorphism, orientation preserving, with f of x is y. And why is this? So the point here, this is just the classification of surfaces. Implies that cutting sigma g along x or y, well, gives a surface with 2 boundary components, right? But also, since I'm doing a boundary like that, I should put this, and so there should be 3. Cutting it open opens up 2 boundary components and decreases the genus by 1 because you can calculate the Willy characteristic, right? So we know this, and so this gives this. So we get gluing F is equal to glue together an isomorphism between cut open surfaces. Okay, so we can do that, right? You cut it. You have these 2 non-separating curves. If you cut open the surface, you get the same thing, right? You choose a homeomorphism between them or a diffeomorphism, and then glue them back together, and you get a diffeomorphism taking x to y. Okay, this is a trick that you can prove many results. This sort of tells you why the mapping class group. If you have 2 curves that separate the surface into a genus 1 and a genus 3 thing, they're also a mapping class taking one to the other. You just have to make sure that if you cut open the surface, you get the same thing. That's like a general trick for understanding how the mapping cost group acts on submanifolds of the surface. And so this implies, though, something. So this, of course, implies that if you do, let's see, can I get these things right? It's never clear. So this says that if we do f ty, tx, f inverse is equal to ty, right? It's equal, this should be equal to f of t of f of x, which is equal to ty. And so thus, tx and ty go to the same element of the abelianization. Right? So it's generated by a single conjugacy class of elements. And so therefore, this implies that the abelianization is cyclic. And once the genus is at least 3, you can find more relations inside the mapping class group that force it actually to be trivial. Okay, you just have to find a relation that says that like a product of 4 non-separating twists is the same as a product of 3, and there's something called the lantern relation which lets you do that. But once you know it's cyclic, then you know like every other relation sort of cuts that cyclic group down to something small. And in genus 1 and 2, you get Z mod 12 and Z mod 10, just because there's not enough room for many relations to happen. In any case, though, so the abelianization of the mapping cost group is quite small. The abelianization of the Torelli group is quite large. There's one last feature, which I will say in words now, but I think I will explain more carefully next time. So is that this isn't just a vector space, right? Wedge 3 of H is a representation of the symplectic group. And as I will explain next time, every homology group of the Torelli group is a representation of the symplectic group. And something more is true. So this isn't just, so a priori, this is a representation of sp2gz. But this is better. This is a representation of sp2gq. Okay, what that means is this is what's called an algebraic representation of sp2gz. And so that's what actually we prove about H2 as well, is that it's not just a finite dimensional vector space, but it's actually an algebraic representation of this algebraic group sp2gq. And I'll explain how you, like, what that means, like what other representations are there. There's definitely non-algebraic representations, and sort of what has to be done to prove things like that. Okay, that's where I'll stop.